Here I've got a nice little picture for you to look at. We've got an angle in standard position. The initial side lays along the x-axis. The terminal side is just sticking out here into space. And of course, these two axes here, these two arrows that aren't labeled, are the x and y axis. Okay. So, in order to define our trig functions, what we do, I've chosen just arbitrary angle here, this arbitrary angle theta. I've drawn it in standard position. And now what I've done is picked a point on the terminal side of that angle. And these functions, when we actually get to calculating them, you can pick any point you want as long as it lays on that terminal side. Sometimes you will have problems where you're given the point and you're not even given the angle, you're just given that point, because that's really the critical part of these functions, this ordered pair x and y on our terminal side. Later on, we're going to talk about how if you choose that point very carefully, like if we choose a point that's closer to the origin or farther away, or is a distance exactly 1 from the origin, it can make a lot of our calculations really easy. So look forward to that. One of the great reasons for doing this allows us to abstract our notion of trig functions as ratios of the sides of a triangle. We can extrapolate this to cover things that aren't triangles. So, for example, theta, the only theta we've dealt with is between 0 and 90. But, oops, you see, if I have a different angle in standard position that's not a right triangle, it's not between 0 and 90. So this is somewhere between 90 and 180 degrees. We can't, that angle right there doesn't make a triangle, but we can still define our trig functions from that by choosing some point on the terminal side of this and applying our definitions. So it's a very exciting concept, and let me draw this. So we've been dealing only with acute triangles where this angle here is between 0 and 90 degrees. So that's the only thing we've been able to use our trig functions for. And for a long time, that's all geometrists had to work with, back in the ancient Greek days, the ancient Greece. There you go, the days of ancient Greece. So immediately using our definitions, if we had some other angle that's much, so this is an acute angle. Let's say we had some obtuse angle like that. So if that's our angle, we can still draw a triangle there. Now that's not a right triangle, so our earlier definitions don't really apply to this. Right? I can't take the opposite side and divide it by the hypotenuse, because this doesn't have a hypotenuse. Hypotenuse, that only applies to right triangles. So what are we supposed to do? Well, we're going to use our new kind of abstracted trig definitions. And if that's not exciting enough, so we've been dealing with the acute, we've been dealing with the obtuse, or we're about to be able to deal with these obtuse. But one of those beautiful things in mathematics, when you're trying to extrapolate this to this obtuse case, it turns out we can do this for things that aren't even triangles. So if we have some third triangle, or excuse me, some third angle that's so far around, we've come back the other way. What is that? I mean, that's a bad drawing, is what that is. But I can't draw a triangle from this. I mean, I end up like some weird curve shape, and that's not a triangle. Alternately, I could do some straight lines there. But again, we're not looking at a triangle there. All right. There are some ways. You're probably yelling at the screen right now, well, why don't you make this triangle? Well, that's not really using our angle, is it? It's using this other angle. It's related to our angle, but it's not the exact angle. And we'll use tricks like that actually, so don't worry, we will do things like that. But the principle is if I give you an angle that's greater than 180 degrees, like this looks like it's about, I'd say it's about 250 degrees, let's say. We can now calculate that trig function using these new definitions. So that's kind of the purpose behind this, and there's a lot more things we'll be able to extrapolate using these new definitions. So very exciting stuff. Okay. Now, so we've chosen our point xy on the terminal side. That forms a triangle here, right? And we can look at it using this. We're gonna look at the acute case to figure out how this relates to our original definitions. Thank you. But then the techniques we get from this we will use without even drawing a triangle in the future. We'll be able to do that. Okay, so looking at our picture here, and I'll erase this other stuff. We don't need that anymore. In fact, I'll even erase that. So looking at the triangle, looking at the angle from our notes. We started with our initial side. We have some angle that's swept out, theta. We have the terminal side of theta, and we've selected some point on our terminal side. I'll make this a little bigger. Right, and from that we draw this right triangle. Or I've drawn this right triangle in your notes. Okay. And the reason I drew this triangle is again to kind of relate this back to our initial definitions. Now, this point xy, that determines the length of the sides of our triangle. Right? The x-coordinate is the distance we've gone along the x-axis. So that's the length of this side. Right? This length here is x. We've gone x along that axis there. Now, the y-coordinate tells us how far we've gone in the y direction. So that's the length of that side right there. Now, you know, in order to solve our right triangle here, we also need this side, the hypotenuse. And what is that side? Well, in this case, we don't know because we don't have any, I don't have any numbers here, but I can still come up with a formula for it. This side we're going to call the radius for reasons that maybe aren't the easiest to explain right now. Oh, I don't know. I guess, well, anyway, we're going to call this side the radius. And it's related to the radius of a circle. How can we calculate it? Well, we're talking about this length here along the hypotenuse. How do the lengths of the legs of a triangle, a right triangle, relate to the hypotenuse? Let me draw that a little nicer. So that distance there, we don't know what that is. We're going to call it R. And we've got a nice simple formula for it. It's the square root of x squared plus y squared. So that's just the Pythagorean theorem. We've solved it for the hypotenuse there, and that allows us to come up with this little formula. Okay, and we will use that over and over again. We will use that probably more than you think we would. We'll use that a lot to solve these triangles from here on out. Even for obtuse triangles, and for things we can't even draw as triangles, we're going to find x, y, and r, and then use these definitions. Now, these definitions I keep referring to, they're here in your notes. The sine of our angle is y over r. And you see that that relates, that's our same definition we've been using. Let's switch to green. Okay. Sine of our angle theta is y over r. But that's the same as it's always been. That's our same definition. We've got our angle. Y is the opposite side. So it's still the opposite side. We're just calling it y. So sine was opposite over hypotenuse. It's still going to be opposite over hypotenuse, but now it's, for the hypotenuse we're using this new variable r. So instead of being opposite over hypotenuse, we're going to say it's going to be sine is y over r. So there's our new definition. And while you're learning these, I would encourage you to draw out these triangles for these angles, and just think, okay, opposite. What distance is that? Well, I'm going in the y direction. That's my y value. So it's going to be the y value of your point. So on. What is this distance? Well, that's the x value of my point. I can label that distance. And then you can just use your same trig definitions that you've got memorized. So we've got sine is y over r. Cosine is x over r. Tangent is y over x. We've also got our other trig functions, secant, cosecant, and cotangent, but I normally don't talk about those that much because in reality, this is what we primarily use. And when we talk about reciprocal identities and our fundamental identities, I'm going to come back and start using it a little bit more. That's when I'm going to really talk about these things. Because I don't want to say they're not as useful, but I will say that they're essentially these three. They're not fundamentally different in any exciting way that I'm interested in, at least. So that's it. That's our definitions. So I already mentioned a little bit, about why this is so useful for us. It allows us to calculate things we can't make triangles out of, like 0 degrees, 180 degrees, or anything bigger than 180 degrees. Yeah, I mentioned that one specifically, 180 degrees, because that's not an obtuse triangle. That's not an acute triangle. You're going to have a hard time making anything around 180 degrees. But you're welcome to try it. I mean, draw a 180 degree angle. We've got our initial side. We're going to say this is our vertex right here. And we go 180 degrees. Now draw me a triangle connecting this to this. You're going to have some trouble doing it. Now, using our new definitions, if we choose some arbitrary point, x, y, we've got almost everything we need in order to do this. We've got x, we could calculate that part. We've got y. We've actually got y and x. We could calculate the tangent just using those, once we've chosen that point. The thing we don't have r. We can still use this to find r based off of whatever point we get. And then we could find all of our trig functions. Even though we're not able to draw a triangle using these definitions. And this is part of the definition. And you have to know this as well, that the radius is square root of x squared plus y squared. If you know that, then you can calculate these even if you can't draw a triangle. So that's really the main power of these. Okay, so moving on, let's do an actual example of this. Okay, example 1, the terminal side of an angle theta in standard position passes through the point 815. Find the values of the trigonometric functions of that angle. So that's nice. I mean, I can use this thing I have drawn up here. That's really nice for me. I don't have to erase everything. Although at this point, I basically have erased everything. In fact, I might as well. We need to practice at this anyway. Sorry. So I'm going to point 815. 1, 2, 3, 4, 5, 6, 7, 8. And then 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so there is the point that they've given me that's on the terminal side of my angle. They didn't tell me what my angle is. That's okay. I don't need it. My definitions don't require it. I can find the sine of this angle even if I don't know the angle. If I knew the angle, it would be really nice. I could just plug that in my calculator and get at least an approximation. So there is this. Really, this is all I need. I've got my y and my x. I didn't really even need to graph this, but I want you to get in that habit of doing this for a little while to kind of think about where this thing is, to think about how large the angle has to be, things of that nature. For example, I know this is an acute angle. I know it's in the first quadrant. I know that I could draw a right triangle here and use my old trig definitions to solve this thing. So I know a lot about this just from graphing it, so it's a good habit to get into. Okay, if I were to draw my triangle, I'll go ahead and do that. Okay. It's not a very good box there. Better? Okay, kind of. So now you're using this. I know I've gone 8 in this direction, so I know that side is 8. I know I've gone 15 in this direction. Right. So maybe just by seeing that you think, okay, I've got two sides of my triangle. That reminds me that this is a hypotenuse. I can use the Pythagorean theorem on this. Okay. But if you didn't draw this, you still need to know how to do it. You could do it without even drawing this triangle. So how do I find my radius, my last side here? That's a good question. I'm going to have to come over here and do it. I don't have enough room. R equals the square root of 8 squared plus 15 squared. That's 64 plus, I'm not sure what 15 squared is. Ooh, but I got a new emulator. I got a new calculator emulator. Okay, so I could put this in my calculator. So I can do it one step at a time. 15 squared, that's easy enough. It's 225. And that's square root of 289. I wonder if that has a square root. I'm going to go out on a limb here and say it doesn't. We'll try it anyway. Square root of 289. That gives me 17, so it actually worked out really nicely. Oh, this is one of the main reasons I like this tool. It displays what buttons I'm pressing in case you're having trouble following along. So it's really awesome little program there. And clear that, clear this. Now I could have just entered that all at once. So square root of actually, let me clear that. Well, let me clear this. Clear that. There we go. So second square root 8 squared plus 15 squared equals 17. So that worked out really nicely. Okay, and that gives us the last piece of our puzzle here, 17. Oops. So now that we've got our radius, 17, now it's really easy to find our trig functions. This is 15 over 17, right? It's y over r, y over r. X over r is just 8 over 17. And then y over x is 15 over 8. Okay. So, I mean, that's really it. Take the time to really get this down. Being able to calculate r, and then from r, use that to find your trig functions, and make sure you've got these things memorized really well. And then that's over half this class. No, I would say that's over half this class. Just being able to calculate these things. And I'll do another one here where it's not a nice simple acute angle. So let's do that. Example 2. That's the only way to really make this more complicated is for me to give you something that you can't graph. But you don't need to graph it. I mean, this picture didn't really, we didn't really use it for anything. I always liked drawing that growing up because it helped me make sense of this. It helped me relate it to our original definitions. I have a really bad memory, so I don't like to have to memorize multiple sets of definitions. And that really helped me to memorize it, to see that this is the same set that we already learned. Okay. So, number 2, the terminal side of an angle theta in standard position passes through the point -3, -4. Now, I am going to graph this, because again, you need to get used to graphing it just to help visualize what quadrant this is in. So our x-axis, this is our x-axis, this is our y-axis, and our point is -3, 4. So that first coordinate tells me I'm going in the negative direction of the x-axis. That's right there. And then the second, that -4, that is going along the y-axis. -4 tells me to go down 4. Okay. So there's a point on the terminal side of my angle. There's my initial side. I draw my angle around here to that terminal side. Okay, and there's my unknown angle theta. It's this angle I swept out. So I can't draw a triangle from that easily. Later on we actually will draw triangles from this, but we'll get there, just not today. Just a little bit about this thing. Again, we know this point, -4, or sorry, -3, -4. We know some stuff about this. We know this is in quadrant 3. And just in case you don't remember your quadrants, I'll go ahead and label those. Quadrant 1, quadrant 2, quadrant 3, quadrant 4. So you notice our quadrants are labeled in the same direction we're moving our angle. It's in the counterclockwise direction, and this is kind of the reason why. Well, you could argue that this is the reason why. Okay. So some general knowledge about this. Some people like memorizing things in terms of quadrants. So if you're like you, then it's going to be really easy to draw this and see which quadrant it lies in. So some things that we're going to see in this problem that are different from the last. We've got these negative signs. So we're going to have to, that's going to change some things. And we're also going to see something else about our one remaining variable. We're going to see something about r in just a second here. In fact, we're going to see it right now because we're going to find r. I'll pick another crazy color. Let's go with red this time. Let me write this out. Remember, r is our x-coordinate squared plus our y-coordinate squared. Okay. Now, I wrote this in parentheses for a very specific reason. If any of you came through our algebra program here at USM, you're probably familiar with that. Excuse me, if you took it here on campus. I know a lot of our instructors kind of spend some time on this because it's kind of emphasized in our curriculum. Hopefully your instructor did. But we have to square this negative, right? We have to square that along with the 3 because otherwise we're going to end up with a negative value here. So let me tell you what I mean. To square something means to multiply by itself, right? So I want to multiply -3 by -3. And what happens when I multiply negative by negative? I get a positive. So I end up with a positive value. So that's why it's really important when you think about this. You're squaring that entire x value. So you're squaring that entire -3. So you're taking that -3 and multiplying it by -3. So -3 squared is 9. -4 squared is 16. 9 plus 16 is 25. And the square root of 25 is 5. So that was our one bit of calculation we need. Now that we've got that, we can find each of our trig functions. Sine is y over r. What was our y? Well, they gave it to us as -4. And our r is 5. So -4 over 5. We can't simplify that any. We're good to go. Cosine is x over r, so -3 over r was 5. And then finally, tangent, y over x. Well, we could have done that one from the beginning. -4 over -3. And that's a positive 4/3. Right, we do have to simplify that. A negative by a negative, just like a negative times a negative, is a positive. So there we go. Okay. So those two examples should be plenty to get you started on this. Spend some time thinking about this. Spend some time memorizing it this week, because you don't have a whole lot of assignments to do. Mainly just letting these definitions sink in and play around with it. See what happens. I gave you another one to try here, but I don't think I'm gonna actually. Oops. Yeah. I want you to think about it more than actually. I'm more concerned with you thinking about it than doing the calculation. Here I've given you this point -1, 0. Okay. I say graph that point. So you need to think about this. Where is that point? Where is the point -1, 0? My x value is -1. My y value is 0. Stop the video real fast or pause it and see if you can do these things. Draw this angle in standard position, and then can you do you know what angle that is? So do it seriously. I'll wait. Are you paused yet? Okay, I'm assuming you paused it and went through all that. So here we go. Point 0, -1. I should have drawn this a little bigger, huh? That's kind of a weird graph. I drew some really large tick marks. I just wanted to kind of spread this out a little bit. So the point -1, 0, I've gone -1 in the x direction and nothing along the y direction, in the y direction. So that's this point right here, -1, 0. The question is, what angle is that? Well, we looked at one of these today. There's my initial side, my terminal side has to pass through that point they gave me. And my angle is the thing swept out from my initial side to the terminal side. What is that angle? That's a weird angle. What angle is